Hello. So I'm mainly interested in the fatigue of AM parts, but I use CT to sort of help and eventually sort of predict where things will break. So yeah. So I'm focused on linking process parameters to fatigue life in AM parts. I'm using, as when you fatigue something, there are likely failure points based on the pore size and stuff, and knowing that beforehand is very, very useful in terms of knowing how long your sample is actually going to last. So I'm also comparing that with SEM and optical as well in a way we'll come back to in a minute. So I'm going to talk about 3 different samples that I've manufactured and how that goes in. So we've got anti-manufactured samples that are done via LPBF, data powered bed fusion, that are based on a literature review of CT data. Sorry, CT samples that have been CT'd. We've got an AM sample based on manufactured settings, which is the Renishaw, and wrought samples, which are just basically as solid as you can make them. So at the bottom, to also help, also help prediction, I have lasered holes into some of the samples so to help me predict fatigue. So, just a quick little slide on the CT used. So it's School Geosciences one, and it's a home-built one actually. But anyway, so when I look at the CT data in the literature of fatigue samples, there's a lot of sort of like inconclusive stuff in regards to how they actually CT their data. So this graph here. So I've gone through the literature, I've taken a bunch of samples, and if you see the grey, that's what the literature, sorry, not the grey, the red, yellow, is what the literature data says the CT, says the porosity is. I have recreated these, CT'd them myself, and also Archimedes them, and optical them, having them SEMing them and measuring them. And you can see there's a large range in what some people in the CT community say, what I myself get, and then comparing that to other ones. So in terms of predicting what my samples are going to be in terms of pore sizes, it gets a little bit, what method should I be using, how much can I trust other people's results just based on what they're saying, sort of thing. So to help sort of understand the differences, I've created what I call the RCO, the resolution check object. So this is just a wrought sample that I've lasered. You can see the laser things there. Each of those grids is a repeat of the other ones, just so I can have multiple versions. And then on the left of the table, you can see the intended sizes of them. So 10, 20, 40 centimeter microns. There's 30 in each one. And then that data, that sample was CT'd and sent out to a number of different researchers who all CT'd it in their own ways. So the blue bars are those holes measured under the SEM as a comparison, because I felt like I need to have something which I've determined is the real answer. There's some questions there, but the SEM is the best to have for the moment. And you can see there's 7 different users. And so there's different sizes of holes. The 40 micron, 75 micron, and the 100 micron at the bottom. And just from these graphs, you can see that different people using different methods of analyzing the CT data are coming back with, in some cases, vastly different, down there, that one, vastly different results on how big each individual pore is. So these numbers here are my sort of identifiers for which pore is which. So you can generally see that under SEM, we're pretty consistent in terms of how big the pores are, but there is a range of, for example, this one, 75 microns. Some people are reading some of them at 120, some of them are reading down at 80, and this person here couldn't even see this pore. So that just leads, if I want to be able to predict fatigue life based on the pore size of a pore in one of my samples, how I'm doing it is, how I actually stand this is very important, because there's a large range. just to also mention that these 7 users, there's quite a difference in CT experience. So I know that some people have got like at most 1 years of experience, and then some of them have 15 plus years of experience. So I will also, so it's just sort of interesting to, well, it's complicating things in terms of my prediction. So here's another one where these are Renishaw settings, where again, they've done, so there have been 3 different samples. That the correct energy is what Renishaw suggests you make it at, and then you've got low energy and high energy, so just putting in more energy when you make the samples. So on the y-axis, you've got the velocity of those samples, and then it's analysed by the different users. And in this case, you can see that, for example, user 1, the red, thinks that the high energy is the lowest velocity, so the best sample in this case, whereas green thinks it's correct energy. So even there, there's also, not only is there differences in what size an actual pore is, there's differences in the porosity fraction value of a sample, which further complicates, have I made a good sample or have I made a bad sample, basically. Different people will say different things. It's not a massive difference, but still, it's within. Anyway, so, these are the fatigue samples I'm dealing with. So, you can see some of the settings there, and the Renishaw ones are pulse lasers, so they're a little bit different, but you can see the settings that they've been created under. And so I'm doing a stress range of 300 to 800 megapascals, depending on the samples, frequency of 20 Hz, and an R ratio of -1. So, what these graphs are, these are 2 examples of the volume of pores at any individual slice, and the X value, the X indicates where they've broken. So, this is CT data, and in general, you'd expect that the sample would break at the slice of the highest porosity, but that is not, especially not that one over there. It's not really the case. It's more about the individual pore, its size and its location, especially if it's on the surface. It's a worse in terms of fatigue life. So going back to the previous slides, knowing how big that pore is and its location is very important, and you've already seen that there's a lot of sort of like the differences between different people's visions. So I mentioned before that some of them had been, so from the resolution check object which we lasered and CT'd, that lasering was also done on the sides of some samples. So you can see it there on the left before breaking. You can see the holes, and on the right, this is after breaking under SEM. Down at the bottom, it's 2 lasered holes to sort of see how much. Well, if one pore will obviously break it, but does 2 pores close together, do they act as 1 pore, do they act as 2 pores, or some? So normally when you do this, you do a SN curve, which is just an example of one set of samples I have from the actually manufactured ones. The arrows indicate that those ones didn't break, so I have to, after a million cycles, I haven't broken, so I have to test those a bit more. But this graph is probably giving you a bit more detail where we have the pore size actually on there. So you could measure that pore size via CT, via SEM after it's breaking, of course, and you can get a better indication of exactly what kind of pore you're looking at in terms of breakage. So obviously there is some difference. So there's got some big pores down here which have lasted quite a while, whereas a lot of the other ones are sort of not lasting as long. But generally you'd expect a big pore to sort of break early, but it may also be position based as well on some of them. So another thing to do is to stress intensity factor. So this is generally, so you've seen that one, which is just stress. So that's just one number, whereas this will take into account the pore size, diameter of the pore, depth of the pore, not depth, no. And it can give you a graph like this. So this one is, so again, you can sort of, if you trust the CT readings you're getting of the pore, you can sort of predict, there's a decent curve there, you sort of predict where it's going to break before you even break it, which is useful actually. Yeah. Okay, so we've got, for the RCO, we've got a pit identification rate, success rate of 70 to 100% across the range. 100% of the larger, higher size of pores. Well, 90%, 75% above. So basically what as I said, I'd like to be able to predict, but if I'm, a lot of the prediction would work with more data, but the most data I can get is obviously from the literature. But if I don't know how people have scanned them, or I don't know, or I'm having some distrust, that's a strong word, but in their answer, then it makes it difficult to actually put a lot of data into and come up with a potential equation to predict things. So standardization feels like it would be very good. Just because I will say, when I go through the literature, a lot of them will just say we just CT scanned it. They don't tell you how. They don't tell you exactly what they did, and that makes it a lot more difficult for me to do things. And then with the so I know I can produce. So we can produce simulated surface pores, and then look at them, and then I can predict stress. I can get fatigue life better with the SIF rather than stress alone. So pore size is a key to understanding the fatigue. Variation in pore size can lead to variation in results.